Hello.
Hello, can you hear me?
Yeah.
Okay.
Are you going to share something?
Sure. Yeah, let me share my screen. Okay, let's see. Are you able to see my screen?
Yeah.
Okay.
Yeah, it will be.
Okay. That's good. Yeah, let me know when to begin.
Recording.
You can start.
Okay, great. Right. So last time we talked about definitions of tessellations and triangle groups, focusing on the hyperbolic case. And today I want to continue that by giving more examples. And I also want to touch upon another model of hyperbolic space that we skipped last time, and just some important things that weren't covered last time. I'll also talk a little bit about other tessellations. So when delta, if you remember from last time, which we used to define the triangle groups, when delta is not necessarily negative, and then you have Euclidean or spherical tessellations. So let's begin. So recall from last time. We have this disk model where we have B2 as usual. And we have the hyperbolic metric, which is V hyperbolic is just your usual Euclidean norm divided by 1 minus a square minus b square, where your vector is a plus bi. So unless I mention I'm using another model, we'll stick to this case. And then let's just start talking about some specific cases. So this is a well-known tessellation. So the chessboard tessellation. So what do? You basically tessellate the plane, the Euclidean plane, with squares. And what you do is that for this tessellation, you associate a subgroup. So to a subgroup T, which is a subgroup of all T of group of all all possible Euclidean motions. And so the correspondence is as follows. So you have a square in the tessellation, and it corresponds to an element of your group T. And what is T? So T basically consists of translations. So T is this set, translations, T and M, where each T n comma M is defined as this motion, which sends Z to this guy here. And N M just range over all integers. So 0 plus minus 1, plus minus 2, and so on. Okay, and then I guess I should mention that how can you go back and forth between the tiles? So each square is going to be the image of this tile, which we denote by S00, which is basically everything where X is between 0 and 1, and Y is also between 0 and 1. And of course, it's the image of this S0 under the action of these translations. Right. And so once we have this, it's natural to think that all tessellations with these motions that take one tile to the other will form a group, but it's not true. So caution, the tessellations with these motions that taking tiles to each other need not form a group, which is a bit weird, but it's possible. And the one of the simplest example, or rather counter example, is let's see. So you look at this. So you look at consider a tessellation with these triangles with isosceles right angled triangles and as each tile. And then if you align it appropriately by choosing appropriate alignment, one can show that you don't get a group. Okay, this I'll leave this as an exercise, but it's good to know this. Okay, and then let's go back to what we talked about last time. So triangle groups. So how did we define this? We took this 3 tuple inside of Z larger than 2, and then the delta is defined in terms of these integers. Sorry, -1. And then we have various cases depending on values of delta being positive, 0, or negative. And this is the spherical case, Euclidean, and the non-Euclidean or hyperbolic. Right, and so the picture is going to look like this. Maybe let me draw it here. So we have this triangle, and then the angles are pi over n, m, and l, and then the opposite sides are n0, l0, and m0. Okay. Right. And we write the reflections in these sides, L0, M0, N0 as LMN. So let me maybe write that. So writing LMN as reflections in the sides, L naught, M naught, N naught, we get a group, namely the LMN generate this group, T star from last time. And the words of even length in this, in T star form T element. Okay, and so what I forgot last time is that this is independent of the ordering. So you have TLMN is the same as TMLN, which is the same as TMNL. And one can show this by just looking at the presentation of the group and using various relations to move around things. So it's a purely algebraic exercise. Also recall that this is the Fuchsian group. So TLMN was the Fuchsian group with signature LMN0. Okay, so that's a very good fact. And more explicitly, we had this relation. T star was given by LMN, where each square is 1, and LMN is ML is NLM is 1. And then the words of even length, that is the normal subgroup TLM, is given by these special generators in terms of the LMNs as follows. So you have AN is BL is ABN is 1. Right. Okay. So now that we've talked and reviewed triangle groups, let's talk about some examples. Like I said, I'll focus on delta being positive or 0 as well. And we'll of course discuss examples of hyperbolic tessellations in the end. But right, so let's talk about this group. What do I want? Right, 2, 3, 6, which is the same as T632 by the explanation before. And note this is Euclidean because 1/2 plus 1/3 plus 1/6 is 1. And then, so this is generated by some Euclidean motions. Let's write those as A and B. And in fact, we know precisely what these motions are. So A is given by this Z prime is epsilon Z, where epsilon is E to the, it's a rotation pi/3. And then B is given by Z prime minus 1 is epsilon square Z minus 1. Okay, and so if you want to write out this group, then it would be AB such that A6 is B cube is BA square is 1. Okay. And then one can ask several questions about this group. So recall last time we discussed fundamental regions that kind of take one element from each orbit of the action. And so the fundamental region of this is going to be a quadrilateral. Whose vertices are 0, and they are basically described in terms of this epsilon 1/2√3. Okay, and then if you look at delta specifically, that is the triangle with angles pi/2, 3, and 6, then vertices of delta are a subset of these vertices. So vertices of delta, that is the triangle with angles pi/2, 3, and 6 are basically 0, 1/2, and 1. And this is the, or like, I guess I should say, they form the fundamental region for your group T star 623. And the quadrilateral, did we give it a name? Let's call it Q. Then this quadrilateral Q is going to be delta union delta prime, where delta prime is the reflection of delta inside of your real line. And Q will give you a tessellation of the plane. So you take the fundamental region of T star, you reflect it, and then you get the tessellation. Okay, let's see. Maybe I want to discuss T33 next. So this also has delta equal to 0. And this is in fact a subgroup of index 2. So it's normal inside of T236. And in T333, the canonical fundamental region is a rhombus. So it looks kind of like this. So you have 0, you have 1, and then you have epsilon square, epsilon, something like that. And then, of course, you can write out the generators like before. So the generators of T333 are these motions, AB, corresponding to these motions. Z prime is epsilon Z, and Z prime minus epsilon is epsilon square, Z minus epsilon. Okay, so we can describe it very explicitly. And then one can also look at this group, which is T244, but it's not that interesting because it's basically very similar to the chessboard tessellation, that is the one with the squares that we talked about in the beginning. Okay. Right. So now I want to move on to some spherical cases. So let's see. So we'll talk about dihedral, icosahedral, and so on. So let's begin with the dihedral group. So what is this? This is T2 to N, and then let's see what delta is. That's the starting point. So delta is basically a triangle on the sphere. And it has these 3 vertices. 3 vertices are given by V1, V2, V3, where V1 is basically, you can think of it as one pole of the sphere, so south pole of sphere. V2 is, say, Z equals 1, and V3 is Z equals this E I pi N. And then, let me see if I can add a page. Okay. And so the natural thing to do is you reflect this. So delta prime is the reflection of this triangle delta that we just defined in R. And if you glue them together, then delta union delta prime will give you the canonical fundamental region of your T. Okay, And more precisely, you can write AB as generators of your T. And A is given by this matrix, epsilon 0, 0, epsilon, and B is just this diagonal matrix. And observe that we have very nice relations. So AN is B square is negative identity. And we can describe these motions. So what is A? A is just a rotation by an angle of 2 pi over n with z equals 0 as a fixed point. And then B is a z prime equals I over iz, and it's an order 2 rotation. Okay. Right. And I guess I should mention z equals 1 is fixed under this, fixed under B. And sorry, is there a question? I thought I heard something. Maybe there's something in the chat. Okay.
Neelima, have you
Yes.
seen the Coxeter's book on geometry?
Uh-huh.
That book in detail describes all these groups, and so you may take them for granted, I think.
Okay. So sorry, I'm having a little bit of trouble hearing you, but yeah.
He considers orientation preserving groups, orientation groups involving orientation reversals, and really classifies them. That's a beautiful chapter in Coxeter.
I see. Okay, okay.
HSM Coxeter. The book is geometry. Book is just
I
called
see.
geometry.
Okay, okay.
That's
Thank
what I
you for
remember.
the.
There may be some other places too, or maybe on internet now they are possible. Yeah. So these are the spherical
Okay.
ones, and we talked about the Euclidean ones, and now the hyperbolic ones. They are infinitely many.
Right.
Yeah.
Right. Yeah. Yeah, there's definitely more restrictions when we are Euclidean. Yeah, yeah, correct. Okay, thank you for the suggestion. And right, and then last thing is if we take delta union delta prime under the action of these motions of your sphere by this group generated by the motions A and B that we just described, we get right. So if we look at the union, then this this gives you a tessellation of the sphere. Okay. Right. So this is the dihedral group, and yeah, there's also nice groups as you go higher. So there's the tetrahedral group. Let's see. I guess I should just use this. Right. So this is T332. So let's start by seeing what delta is. Delta is the triangle with angles pi over 3, and pi over 2. And this again will give you a tessellation of the sphere. And then one may wonder how you obtain this tessellation or why it's called tetrahedral. So there's a procedure. So you begin by inscribing a regular tetrahedron inside a sphere. And once you do this, then you mark the vertices of the tetrahedron and the projection of the centers of its faces. And then you also mark the midpoints of the edges. So you mark these various points on the sphere. And whenever you project, you take the center of your projection is taken to be the center of the sphere, basically. Okay, and then if you do repeated reflections, in the sides of your delta, you get T star. So more precisely, sorry, is there a question?
Yeah. Can you drop this picture?
Sorry, I think there's some audio issue. Can you drop what?
Yeah, I'm asking you.
Please, can you put it in the chat? I'm having trouble hearing for some reason. Mm. Oh, okay. Which example is this?
He's asking the tetrahedron.
Oh, the tetrahedron. Right. I'm very bad at drawing 3D things, but the basic idea is, I mean, you have like a sphere, and then you're drawing the tetrahedron, and you're just joining everything to the center of the sphere and projecting. Projecting the, I mean, the midpoints of all the edges and the centers of its faces. Yeah. Hopefully that makes sense, but okay, great. Yeah, I think it's better done with some software than done by hand. Right. And we have like a lot to talk about, so maybe I'll skip that for now. Okay. So going back to this group, T star, we have the following presentation. Right, so we have all these relations. And what's nice is it's not just some random group, it's a very familiar group. So this is, one can check by, again, going back and forth with the presentations. This is in fact the permutation group, S4. So it's a nice group. And we can also look at T332, which is given by the following. where A and B are in terms of the LMN defined above. And this is also a very nice group. So this is, I mean, this is index 2. So this is going to be A4. So T332 is in fact A4. So it's all the even permutations. And you can think of this as the group of rotations of sphere that carry the inscribed tetrahedron to itself, to view it as a permutation group. And then if you want to understand what the fundamental region is geometrically, so it's delta union delta prime. And what are the vertices? So you have the two vertices of tetrahedron and the midpoint of a face that contains the vertices. Right. And I guess I want to talk about this as well. So if you write out the generators of T233, then these actually correspond to these conformal maps of C. And you can write them in matrix form as follows. Right. Okay, and AB is this diagonal matrix. And so, so we have a nice understanding of the generators. And another observation is that the motions of the elliptic plane that are generated by these motions, A and B, give a group E332, which is in fact isomorphic to your group T233. And similarly, if instead of viewing it as spherical motions, if you view LMN as these motions of the elliptic plane, then you get a group which is denoted by E star 332, which is in fact isomorphic to your T star 233. Okay. And I guess another word of caution is, although they are isomorphic and you can go back and forth, the fundamental regions are not easily translated. So fundamental regions are not so straightforward. So they're not the same. Why is my pen? Okay, are not the same. So we have to be a little bit careful in this case. Okay, let's move on to the octahedral group. So this is T234. So
Actually, I think to go into this detail.
sorry, please can you repeat that? My audio is really bad.
You will run out of time if you will go in these details. So you have not, you plan to discuss software applications for triangles, right?
Right. I think we have enough time to, we have to end in around 20 minutes.
Yeah.
Okay. Yeah, I think there should be time to,
There's some
let's
example
see.
in the hyperbolic also, right? Hyperbolic signature.
Yes.
Then maybe you can skip these two examples of character and hyperbolic.
Okay. Yeah, that's a good idea. Maybe I can move to the hyperbolic case, but right.
It would be discussed at many places, as Professor Kulkarni just suggested as competitor, usage standard,
Right.
and good details.
Okay. Yeah, that makes sense. Right. So I'll skip the octahedral group, and then there's also the icosahedral group, which is T235. So this is all the elliptic case, and right, as we want to focus more on the hyperbolic case, let's move on to that. So right. Let's see. Okay. Right. So there's one remark I wanted to make is we can construct these tessellations of hyperbolic space. Like a hyperbolic plane, more precisely, by simple polygons that don't correspond to, that are not the canonical fundamental regions of any group of motions, any group of non-Euclidean motions. So it's not necessary that you always have a tessellation given by some fundamental region. And one such example is this group, which we talked briefly about last time, maybe T237. So you have a triangle with angles pi over 2, pi over 3, pi over 7. And it gives you a tessellation that's a subset of the one that's given by quadrilaterals of equal sides. So where by this quadrilateral, I mean, so it looks like this. And one can show that Q is actually not a fundamental region of any group of nice motions, so of motions that send Q to an adjacent such quadrilateral with a side in common. Okay. And then this is an example of what the T star 237 tessellation looks like. And you can see these shaded and unshaded triangles, where each triangle is a fundamental region of T star 237. Okay. Let's talk about T288. So the fundamental region looks like this triangle here. So it's these two triangles joined together, and the vertices are labeled here. And then T264 is another example. The fundamental region has area pi over 6, and you can write the presentation as follows. Okay. And let's see what else. Right, 238 has a fundamental region of area pi over 12. So, right, the area seems to be getting smaller. Like in this case, T288, the area was pi over 2, and then 238 is pi over 12, and T264 is pi over 6. Okay. And I also have a picture for this case. For 238, so if you look at this carefully, you see that it's a 16-gon, and it has 48 copies of delta, which is the fundamental region of your T, 238 that is. And you can see this by looking at the shaded and unshaded triangles, and that is shaded plus unshaded triangles. And then each triangle is a fundamental region of your T star. So, okay, let's see, how are we doing on time? Okay, maybe I should talk about the other model and a little bit about the software that's available. Okay, let me pause sharing for a second. Let's see. Okay, this should work. Right, so let me talk a little bit about the client disk model. So we just model hyperbolic plane in a disk like before, but unlike the Poincaré model which we discussed last time, this is. I'm sorry.
This is by somebody else.
Oh, okay.
Ah.
Right. I will just give a quick review then, because we have an example that uses it. Yeah, I won't spend too much time on this. Right. And right. And so we just have this non-conformal model, which all of you know now, and the metric is given by the following. Right, where the A and B are just obtained by the X and Y by joining the line and seeing where it intersects the disk. Okay, so that's the model, and the example I want to discuss related to it is this one right here, So this is the tessellation of conic by delta with angles pi over 2, pi over 3, 0, and this is in the Klein model. And okay. Maybe I can share the software.
Yeah. There's a link of
Yeah.
that.
Right, yeah. Let
Demonstration.
I'm sorry.
Could you give a demonstration of one example?
I don't know why my audio is so bad today. Please, can you put it in the chat maybe? Yes, yes, I will give a.
Yeah, there's 10 minutes left. Yeah. If you could do that.
Okay, yeah, yeah. Just give me a second to. Um, how should we do this? Right. I'm trying to. Okay, let's see if I can share screen. Okay. Are you able to see this?
Yeah.
Okay, great. Let me see if I can make it bigger. But maybe not this big. Right. Okay, right. So I think this now it's visible. So this is a software developed by a software engineer in Boston, and I think it allows you to choose how many what sided polygon you want, and then how many of those polygons are adjacent to each other, which is shown by this P and Q here. And yeah, and in general, it's a good thing to have holdover. And I think last time Professor Kulkarni mentioned his result, which talks about this PQ type tessellation. But anyway, so if we can, for example, if P is, let's take something small, 3, and Q is, okay, 5. Okay, seems to be Sorry about this. But essentially you can play around with the type of polygon and how many adjacent polygons you have. And it also allows you to switch between the two disk models, which is nice because sometimes you want to view things as they are, which is when you want to use the Poincare model, versus when you want to view things more as lines, then you might want to use the Klein model. But yeah, does anyone want to see a specific example or?
Yeah, there's 236 that you discussed maybe, or 237.
I heard something 7, but please can someone put the example in the chat? So let me close this and oh, 237, okay.
And share the link of that software page, or it is online, right? It is not application, right? Or software.
It's actually
Okay.
an application.
Is there an online calculator type of thing it is?
So it's developed by this person and he's made it open source, but you have to download the software to use it.
Okay. Can you share the link of that in the chat box?
Yes, for sure. For some reason, it's not working well. Maybe I can like
Yeah, just share
do
the
the.
link if I will open here.
Mhm. Yeah, for sure. So I just shared the link. And it seems like there's some, okay.
There is some question also, if you can understand it. Adjust that.
Do we know which of the triangle groups arithmetic? No, the groups are arithmetic. 2, 3, 7 are arithmetic. This 2, 3, 7. So 237 is a hyperbolic group, and
Yeah, it is working at my place, that application that you just sent.
I'm sorry.
The application that you sent us, I just tried and it is working here.
Okay, that's good to know. As long as you can use it, yeah. Right.
To get the Surya's question about arithmeticity, but in the next week we will have this talk on this specifically when the third triangle groups are arithmetic.
Okay.
So then maybe you can wait till the Tuesday and the next Tuesday.
Okay.
Yeah.
Okay.
Yeah, okay, thanks. Yeah. Yeah, I guess I'm more interested in arithmetic, but yeah, okay, thank you, thanks, yeah.
PC7 is actually arithmetic, right?
Sorry, I couldn't hear you.
PC7 is, I think, arithmetic.
Yeah, 237 is related to the, I think it's related to this real field, 2 cosine pi, 2 pi over 7, some Hamiltonians over, quaternions over to that field. But yeah, I guess, yeah, I mean, these are all, I mean, yeah, most of these, if you don't have infinity, these are all co-compact. I don't know much about co-compact stuff. I work more with things which have cusps, and yeah, so, and in that case, only like 2, 3 infinity, 2, 4 infinity, 2, 6 infinity are the only triangle groups that, yeah, I mean, 2, 3 infinity is SL to Z, for instance, but yeah, so that's, yeah.
I think that 2, 6 infinity is not arithmetic. From 5 onwards, it is non-arithmetic in Hackey.
Sorry.
To confirm you.
Oh yeah. So that's what only for 3 values it's arithmetic. Yeah. If it's there is infinity. Yeah, but yeah.
So not even for 6 it is arithmetic, I think.
Not even for 6. Okay. Yeah. There are some 3 numbers which, yeah, maybe 3, 4. I would check what. Yeah.
Okay, Neelima, you can continue if you have something to say.
I'm sorry.
You can continue your presentation, whatever.
Okay, yeah, I mean, we only have few minutes left, so I don't want to start something and right. I'm just thinking about the question. So if we mod out, if you remember the phi sub g that we defined last time, I think it was towards the end of the talk. We define phi sub g as the fundamental group of this Riemann surface pi 4g. But anyways, so if you quotient out T237 by that, then you get PSL2. I don't know if that helps. But...
Okay, leave that question. We will discuss later about it. So
Okay.
you are addressing Surya's question, right?
Yeah.
Okay. We will discuss it later. And,
Okay.
do you have anything else?
I think that's mainly what I wanted to talk about. Yeah.
Okay, then thanks. Nice presentation, and the software was really good and working here.
Thank you. Yeah. Yeah, and people can email me questions if they have more.
So do you know how these programs work also, that you share software? Because you are in the programming, right?
Oh, you mean like how the code was written? I have not looked into it, but I imagine, yeah, like if people are interested in that, I'm happy to help in any way. Yeah.
Hi, I have a question. Can you hear me?
Yes.
I mean, maybe, I mean, for if you're a geometer, maybe this is obvious, but I don't see it. Yeah, so you have these groups, right? So say, let's say you're in the hyperbolic case. Is it easy to see that they tessellate? I mean, like the fact, I mean, you have a triangle and you're just making deflections or rotations. Is it easy to see that there is tessellate?
I don't know what you mean by easy, but you just check you check there's no gaps and there's no overlaps, like the basic conditions for
So yeah, I mean, you are doing some rotations at the vertices and so on, but Yeah. So how do you check that? Yeah, I guess the question is checking that there are no gaps, right? I mean, you have a triangle and you have.
Surya, you have a certain condition on these elements. They have to be
Oh
integer.
yeah. So you're making sure that the angles are multiples of the proper. And I mean you have if you wrote okay, you can fit n of them or some integer number of them
Initially,
at
the
that point.
generators are those reflections that you reflect along the side. And since two reflections make a rotation, so rotations are also generated with respect to the angle, that element n. Okay, so if you take ABC are the reflection, then AB, BC, and CA would be the rotation generator.
Yeah, but I mean, okay, locally at that vertex you can fill I mean you can imagine, okay, so yeah, it's fine. At that vertex the area is filled, but then, okay, one vertex I'm sure, okay, I'm okay, but I don't know what's happening globally. I mean, in the sense that after you add all the triangles at that one vertex, then if you want to add more triangles, how are you sure that you're definitely going to fill and not have gaps? I guess that's okay. Yeah, probably. Okay, I should think more about
This
it.
book maybe that Neelima was main reference, Magnus, and there are many examples done there, and there are many other books. And I think the examples that Neelima was doing, Ashoka as well, and these things, they're quite related with the generalized thermal equations, and I discussed with Neelima. So if you look at the Fitz-Duker's paper on the generalized Fermat equation, so the spherical case of the generalized Fermat equations is solved by these coverings. Okay. So, do you getting my point, Neelima? Did you look at the paper that I shared with you once? So, the spherical case of the generalized Fermat equations is solved by these coverings that comes from the icosahedral and tetrahedral and other things. And so construct a Bailey map from these kind of triangle groups. And it is kind of a hope, means it is this proposal of the government that when we discuss the hyperbolic case of the generalized Fermat equation that is remains unsolved, then we will need these triangle groups and related coverings and other things. So their quotient. So we will keep discussing about this aspect. So these triangle groups actually give rise to coverings that are required for the study of those equations. Okay, Neelima, thank you for coming.
Thank you. Yeah.
It was nice talk and nice presentation.
Yeah, thanks. Yeah.
Have a good day. Bye.
Thank you, everyone.
Thank you.